understand how something apparently impossible can work, or you're trying to do a factor analysis or principal component, you get a rotation that won't converge. It helps to understand what it is about the algorithm that's happening and why that won't work in that situation. And number 3, interestingly, some procedures, some math is easier and quicker to do by hand than by firing up the computer. And I'll show you a couple of examples in later videos where that can be the case. Now, fundamentally, there's a nice sort of analogy here. Math is to data science, as for instance, chemistry is to cooking, kinesiology is to dancing, and grammar is to writing. The idea here is that you can be a wonderful cook without knowing any chemistry, but if you know some chemistry, it's going to help. You can be a wonderful dancer without knowing kinesiology, but it's going to help. And you can probably be a good writer without having an explicit knowledge of grammar, but it's going to make a big difference. The same thing is true of data science. You will do it better if you have some of the foundational information. So the next question is, what kinds of math do you need for data science? Well, there's a few answers to that. Number 1 is algebra. You need some elementary algebra. That's the basically simple stuff. You can have to do some linear or matrix algebra because that's the foundation of a lot of the calculations. And you can also have systems of linear equations where you're trying to solve several equations all at once. It's a tricky thing to do in theory, but this is one of the things that's actually easier to do by hand sometimes. Now, there's more math. You can get some calculus. You can get some big O, which has to do with the order of a function, which has to do with sort of how fast it works. Probability theory can be important. And then Bayes' theorem, which is a way of getting what's called a posterior probability, can also be a really helpful tool for answering some fundamental questions in data science. So in sum, a little bit of math can help you make informed choices when planning your analyses. Very significantly, can help you find the problems and fix them when things aren't going right. It's the ability to look under the hood that makes a difference. And then, truthfully, some mathematical procedures, like systems of linear equations, that can even be done by hand, sometimes faster than you can do with a computer. So you can save yourself some time and some effort and move ahead more quickly towards your goal of insight. Now, data science wouldn't be data science and its methods without a little bit of statistics. So I'm going to give you a brief statistics overview here of how things work in data science. Now, you can think of statistics as really an attempt to find order in chaos, find patterns in an overwhelming mess. Sort of like trying to see the forest and the trees. Now, let's go back to our little Venn diagram here. We recently had math and stats here in the top corner. We're going to go back to talking about stats in particular. What you're trying to do here, one thing is to explore your data. You can have exploratory graphics because we're visual people and it's usually easiest to see things. You can have exploratory statistics, a numerical exploration of the data. And you can have descriptive statistics, which are the things that most people would have talked about when they took a statistics class in college, if they did that. Next, there's inference. I've got smoke here because you can infer things about the wind and the air movement by looking at patterns in smoke. The idea here is that you're trying to take information from samples and infer something about a population. You're trying to go from one source to another. One common version of this is hypothesis testing. Another common version is estimation, sometimes called confidence intervals. There are other ways to do it, but all of these let you go beyond the data at hand to making larger conclusions. Now, one interesting thing about statistics is you're going to have to be concerned with some of the details and arranging things just so. For instance, you get to do something like feature selection. That's picking variables that should be included or combinations. And there are problems that can come up. There are frequent problems, and I'll address some of those in later videos. There's also the matter of validation. When you create a statistical model, you have to see if it actually is accurate. Hopefully you have enough data that you can have a holdout sample and do that, or you can replicate the study. And then there's the choice of estimators that you use, how you actually get the coefficients or the combinations in your model. And then there's ways of assessing how well your model fits the data. All of these are issues that I'll address briefly when we talk about statistical analysis at greater length. Now, I do want to mention one thing in particular here, and I just call this beware the trolls. There are people out there who will tell you that if you don't do things exactly the way they say to do it, that your analysis is meaningless, that your data is junk, and you've lost all your time. you know what? They're trolls. So the idea here is don't listen to that. You can make enough of an informed decision on your own to go ahead and do an analysis that is still useful. Probably one of the most important things to think about in this is this wonderful quote from a very famous statistician that says, all models or all statistical models are wrong, but some are useful. And so the question isn't whether you're technically right or you have some sort of level of intellectual purity, but whether you've done something that is useful. That, by the way, comes from George Box. And I like to think of it basically as this, as wave your flag, wave your do-it-yourself flag, and just take pride in what you're able to accomplish, even when there are people who may be criticizing it. Go ahead, you're doing something, go do it. And so, in sum, statistics allow you to explore and describe your data. They allow you to infer things about the population. There's a lot of choices available, a lot of procedures, but no matter what you do, the goal is useful insight. Keep your eyes on that goal and you will find something meaningful and useful in your data to help you in your own research and projects. Let's finish our data science methods overview by getting a brief overview of machine learning. Now, I got to admit, when you say the term machine learning, people start thinking about something like the robot overlords who are going to take over the world. That's not what it is. Instead, let's go back to our Venn diagram one more time. And in the intersection at the top between coding and stats is machine learning, or as it's commonly called, is just ML. The goal of machine learning is to go and work in a data space. So you can, for instance, take a whole lot of data. We've got tons of books here. And then you can reduce the dimensionality. That is, take a very large scattered data set and try to find the most essential parts of that data. And then you can use these methods to find clusters within the data, like goes with like. You can use methods like k-means. You can also look for anomalies or unusual cases that show up in the data space. Or if we go back to categories, again, I talked about like for like. You can use things like logistic regression or nearest neighbors, KNN. You can use naive Bayes for classification, or decision trees, or SVM, which is support vector machines, or artificial neural nets. Any of those will help you find the patterns and the clumping in your data so you can get similar cases next to each other and get the cohesion that you need to make conclusions about these groups. Also, a major element of machine learning is predictions. You're going to point your way down the road. The most common approach here, the most basic, is linear regression, multiple regression. There's also Poisson regression, which is used for modeling count or frequency data. And then there's the issue of ensemble models, where you create several models and you take the predictions from each of those and you put them together to get an overall more reliable prediction. Now, I'll talk about each of these in a little more detail in later courses, but for right now, I mostly just want you to know that these things exist, and that's what we mean when we refer to machine learning. So, in sum, machine learning can be used to categorize cases and to predict scores on outcomes. And there's a lot of choices, many choices and procedures available. But again, as I said with statistics, and as I'll say again many times after this, no matter what, the goal is not that I'm going to do an artificial neural network or an SVM. The goal is to get useful insight into your data. Machine learning is a tool, and use it to the extent that it helps you get that insight that you need. In the last several videos, I've talked about the role in data science of technical things. On the other hand, communicating is also central to the practice. And the first thing I want to talk about there is interpretability. The idea here is that you want to be able to lead people through a path on your data. You want to tell a data-driven story. And that's the entire goal of what we're doing with data science. Now, another way to think about this is when you're doing your analysis, what you're trying to do is solve for value. You're making an equation, you take the data, you're trying to solve for value. The trouble is this: a lot of people get hung up on analysis, but they need to remember that analysis is not the same thing as value. Instead, I like to think of it this way, that analysis times story is equal to value. Now, please note, that's multiplicative, not additive. And so one consequence of that is when you go back to analysis times story equals value, well, If you have zero story, you're going to have zero value because, as you recall, anything times zero is zero. So instead of that, let's go back this and say what we really want to do is we want to maximize the story so that we can maximize the value that results from our analysis. Again, maximum value is the overall goal here. The analysis, the tools, the tech are simply methods for getting to that goal. So let's talk about goals, for instance. Analysis is goal-driven. You're trying to accomplish something specific, and so the story or the narrative or the explanation you give about your project should match those goals. If you're working for a client and they had a specific question that they wanted you to answer, then you have a professional responsibility to answer those questions clearly and unambiguously so they know whether you said yes or no and they know why you said yes or no. Now, part of the problem here is the fact that the client isn't you and they don't see what you do, and as I show here, simply covering your face doesn't make things disappear. You have to worry about a few psychological abstractions. You have to worry about egocentrism. And I'm not talking about being vain. I'm talking about the idea that you think other people see and know and understand what you know. That's not true. Otherwise, they wouldn't have hired you in the first place. And so you have to put it in terms that the client works with and that they understand. And you're going to have to get out of your own center in order to do that. Also, there's the idea of false consensus, the idea that, well, everybody knows that. And again, that's not true. Otherwise, they wouldn't have hired you. You need to understand that they're going to come from a different background with a different range of experience and interpretation. You're going to have to compensate for that. A funny little thing is the idea about anchoring. When you give somebody an initial impression, they use that as an anchor and then they adjust away from it. So if you're going to try to flip things over on their heads, watch out for giving a false impression at the beginning, unless you absolutely need to. But most importantly, in order to bridge the gap between the client and you need to have clarity and explain yourself at each step. You can also think about the answers. When you're explaining the project to the client, you might want to start in a very simple procedure. State the question that you're answering. Give your answer to that question. And if you need to, qualify as needed, and then go in order top to bottom. So you're trying to make it as clear as possible what you're saying, what the answer is, and make it really easy to follow. Now, in terms of discussing your process, how you did this all, most of the time it's probably the case that they don't care. They just want to know what the answer is and that you used a good method to do that. So in terms of discussing process or the technical details, only when absolutely necessary. That's something to keep in mind. The process here is to remember that analysis, which means breaking something apart. This, by the way, is a mechanical typewriter broken into its individual components. Analysis means to take something apart. An analysis of data is an exercise in simplification. You're taking the overall complexity, sort of the overwhelmingness of the data, and you're boiling it down and finding the patterns that make sense and serve the needs of your client. Now, let's go to a wonderful quote from our friend Albert Einstein here, who said, or if you want another way of putting it, a principle that comes from my field, I'm actually a psychological researcher, they talk about being minimally sufficient, just enough to adequately answer the question. If you're in commerce, you know about a minimal viable product. It's sort of the same idea with an analysis here, the minimum viable analysis. So here's a few tips. When you're giving a presentation, more charts, less text. Great. And then simplify the charts. Remove everything that doesn't need to be in there. Generally, you want to avoid tables of data because those are hard to read. And then one more time, because I want to emphasize it, less text. Again, charts, tables can usually carry the message. And so let me give you an example here. I'm going to give a very famous data set, Berkeley admissions. Now, these are not stairs to Berkeley, but it gives the idea of trying to get into something that's far off and distant. Here's the data. This is graduate school admissions in 1973. So it's over 40 years ago. But the idea is that men and women were both applying for graduate school at the University of California at Berkeley. And what we found is that 44% of the men who applied were admitted. That's their part in green. And that of the women, only 35% were admitted when they applied. So really, first glance, this is bias, and it actually led to a lawsuit. It was a major issue. So what Berkeley then tried to do is find out, well, which programs are responsible for this bias, and then you got a very curious set of results. If you break the applications down by program, and here we're just calling them A through F, 6 different programs, what you find actually is that in each of these, male applicants are on the left, female applicants are on the right. If you look at program A, women actually got accepted at a higher rate. And the same is true for B. And the same is true for D. And the same is true for F. And so this is a very curious set of responses, and it's something that requires explanation. Now in statistics, this is known as Simpson's paradox. But here's the paradox. Bias may be negligible at the department level. And in fact, as we saw in 4 of the departments, there was a possible bias in favor of women. And the problem is that women applied to more selective programs with lower acceptance rates. Now, some people stop right here and say, therefore, nothing's going on, nothing to complain about. But that's still ending the story a little bit early. There are other questions that you can ask. And as producing a data-driven story, this is stuff that you would want to do. So for instance, you may want to ask, why do the programs vary in overall class size? Why do the acceptance rates differ from one program to the other? Why do men and women apply to different programs? And you might want to look at things like the admissions criteria for each of the programs, the promotional strategies, how they advertise themselves to students. You might want to look at the kinds of prior education students have in each of the programs, and you really want to look at funding levels for each of the programs. And so really you get one answer. It leads to more questions, maybe some more answers and more questions, and you need to address enough of this to provide a comprehensive overview and solution to it for your client. In sum, let's say this: stories give value to data analyses. And when you tell the story, you need to make sure that you are addressing your client's goals in a clear, unambiguous way. And the overall principle here is be minimally sufficient. Get to the point, make it clear. Say what you need to, but otherwise be concise and make your message clear. The next step in discussing data science and communicating is to talk about actionable insights, or information that can be used productively to accomplish something. Now, to give sort of a bizarre segue here, you look at a game controller. It may be a pretty thing, it may be a nice object, but remember, game controllers exist to do something. They exist to help you play the game and to do it as effectively as possible. They have a function, they have a purpose. Same way, data is for doing. Now that's a paraphrase from one of my favorite historical figures, and this is William James, the father of American psychology and pragmatism in philosophy. And he has this wonderful quote. He said, "My thinking is first and last and always for the sake of my doing." And the idea applies to analysis. Your analysis and your data is for the sake of your doing. And so you're trying to get some sort of specific insight in how you should proceed. What you want to avoid is the opposite of this from one of my other favorite cultural heroes, the famous Yankees catcher Yogi Berra, who said, "We're lost, but we're making good time." And so the idea here is that frantic activity does not make up for a lack of direction. You need to understand what you're doing so you can reach the particular goal. And your analysis is supposed to do that. So when you're giving your analysis, you're going to try to point the way. Remember, why was the project conducted? The goal is usually to direct some kind of action, reach some kind of goal for your client. And that the analysis should be able to guide that action in an informed way. One thing you want to do is you want to be able to give the next steps to your client. Give the next steps. Tell them what they need to do. You want to be able to justify each of those recommendations with the data and your analysis. As much as possible, be specific. Tell them exactly what they need to do. Make sure it's doable by the client, that it's within their range of capability, and that each step should build on the previous step. Now, that being said, there is one really fundamental sort of philosophical problem here, and that's the difference between correlation and causation. Basically, it goes this way. Your data gives you correlation. You know that this is associated with that, but your client doesn't simply want to know what's associated. They want to know what causes something. because if they're going to do something, that's an intervention. It's designed to produce a particular result. So really, how do you get from the correlation, which is what you have in the data, to the causation, which is what your client wants? Well, there's a few ways to do that. One is experimental studies. These are randomized controlled trials. Now, that's theoretically the simplest path to causality, but it can be really tricky in the real world. There are quasi-experiments, and these are methods, a whole collection of methods, that use non-randomized data, usually observational data, adjusted in particular ways to get an estimate of causal inference. Or there's the theory and experience, and this is research-based theory and domain-specific experience. And this is where you actually get to rely on your client's information. They can help you interpret the information, especially if they have greater domain expertise than you do. Another thing to think about are the social factors that affect your data. Now, you remember the data science Venn diagram. We've looked at it lots of times. It's got these three elements. Some people have proposed adding a fourth circle to this Venn diagram, and we'll kind of put that in there and say that social understanding is also important, critical really, to valid data science. Now, I love that idea, and I do think that it's important to understand how things are going to play out. There's a few kinds of social understanding. You want to be aware of your client's mission. You want to make sure that your recommendations are consistent with your client's mission. Also, that your recommendations are consistent with your client's identity, not just this is what we do, but this is really who we are. You need to be aware of the business context, sort of the competitive environment and the regulatory environment that they're working in, as well as the social context. And that can be outside of the organization, but even more often within the organization. Your recommendations will affect relationships within the client's organization. And you're going to try to be aware of those as much as you can to make it so that your recommendations can be realized the way they need to be. So in sum, data science is goal-focused. And when you're focusing on that goal for your client, you need to give specific next steps that are based on your analysis and justifiable from the data. And in doing so, be aware of the social, political, and economic context that gives you the best opportunity of getting something really useful out of your analysis. When you're working in data science and trying to communicate your results, presentation graphics can be an enormously helpful tool. Think of it this way. You are trying to paint a picture for the benefit of your client. Now, when you're working with graphics, there can be a couple of different goals. It depends on what kind of graphics you're working with. There's the general category of exploratory graphics. These are ones that you are using as the analyst. And for exploratory graphics, you need speed and responsiveness. And so you get very simple graphics. This is a base histogram in R, and they can get a little more sophisticated. And this is done in ggplot, and then you can break it down in a couple of histograms, or you can make it a different way, or make them see-through, or split them apart into small multiples. But in each case, this is done for the benefit of you as the analyst understanding the data. These are quick, they're effective. Now, they're not very well labeled, and they're usually for your insight, and then you do other things as a result of that. On the other hand, presentation graphics, which are for the benefit of your client, those need clarity and they need a narrative flow. Now, let me talk about each of those characteristics very briefly. Clarity versus distraction. There are things that can go wrong in graphics. Number one is colors can actually be a problem. Also, three-dimensional or false third dimensions are nearly always a distraction. One that gets a little touchy for some people is interaction. We think of interactive graphics as really cool, great things to have, but you run the risk of people getting distracted by the interaction and start playing around with it, going like, ooh, I press here, it does that. And that distracts from the message. So actually, it may be important to not have interaction. And then the same thing is true of animation. Flat static graphics can often be more informative because they have fewer distractions in them. Let me give you a quick example of how not to do things. Now, this is a chart that I made it in Excel, and I did it based on some of the mistakes I've seen in graphics submitted to me when I teach. And I guarantee you everything in here I have seen in real life, just not necessarily combined all at once. Let's zoom in on this a little bit so we can see the full badness of this graphic. And let's see what's going on here. We've got a scale here that starts at 8, goes to 28%, and is tiny, doesn't even cover the range of the data. We've got this bizarre picture on the wall. We have no axis lines on the walls. We come down here, the labels for educational levels are in alphabetical order instead of the more logical higher levels of education. Then we've got the data represented as cones, which are difficult to read and compare, and it's only made worse by the colors and the textures. You know, if you want to take an extreme, this one for grad degrees doesn't even make it to the floor value of 8%. And this one for high school grad is cut off at the top at 28%. This, by the way, is a picture of a sheep, and people do this kind of stuff, and it drives me crazy. If you want to see a better chart with the exact same data, this is it right here. It's a straight bar chart. It's flat. It's as simple. It's as clean as possible. And this is better in many ways. Most effective here is that it communicates clearly. There's no distractions. It's a logical flow. This is going to get the point across so much faster. And I can give you another example of it. Here's a chart I showed previously about salaries for incomes. I have a list here. I've got data scientists in it. If I want to draw attention to it, I have the option of like putting a circle around it. And I can put a number next to it to explain it. That's one way to make it easy to see what's going on. But you don't even have to get fancy. You know, I just got out a pen and a Post-it note and I drew a bar chart of some real data about life expectancy. This tells the story as well that there is something terribly amiss in Sierra Leone. But now let's talk about creating narrative flow in your presentation graphics. To do this, I'm going to pull some charts from my most cited academic paper, which is called A Third Voice, a review of empirical research on the psychological outcomes of restorative justice. Think of that as mediation for juvenile crimes, mostly juvenile. And this paper is interesting because really it's about 14 bar charts with just enough text to hold them together. And you can see there's a flow. The charts are very simple. This is judgments about whether the criminal justice system was fair. The 2 bars on the left are victims. The 2 bars on the right are offenders. And for each group on the left are people who participated in restorative justice or victim offender mediation or mediation for crimes. And for each set on the right are people who went through standard criminal procedures. It says court, but it usually means plea bargaining. Anyhow, it's really easy to see that in both cases, restorative justice bar is higher. People were more likely to say it was fair. They also felt that they had an opportunity to tell their story. That's one reason they might think it's fair. They also felt the offender was held accountable more often. In fact, if you go to court on the offenders, that line's below 50%, and that's the offenders themselves making the judgment. Then you can go to forgiveness and apologies. And again, this is actually a simple thing to code, and you can see there's an enormous difference. And in fact, one of the reasons there's such a big difference is because in standard court proceedings, the offender very rarely meets the victim. Now, it also turns out that I need to qualify this a little bit because a bunch of the studies included drunk driving with no injuries or accidents. When we take them out, we see a huge change. And then we can go to whether a person's satisfied with the outcome. Again, we see an advantage for restorative justice. Whether the victim is still upset about the crime, now the bars are a little different. And whether they're afraid of re-victimization, that's over a 2-to-1 difference. And then finally, recidivism for offenders or re-offending. And you see a big difference there. And so what I have here is a bunch of charts that are very simple to read, and they kind of flow in how they're giving the overall impression and then detailing it a little bit more. There's nothing fancy here. There's nothing interactive. There's nothing animated. There's nothing kind of flowing in 17 different directions. It's easy, but it follows a story and it tells a narrative about the data. And that should be your major goal with presentation graphics. In sum, presenting, or the graphics that you use for presenting, are not the same as the graphics you use for exploring. They have different needs and different goals. But no matter what you're doing, be clear in your graphics and be focused in what you're trying to tell. And above all, create a strong narrative that gives a different level of perspective and answers questions as you go to anticipate a client's question and to give them the most reliable, solid information and the greatest confidence in your analysis. The final element of data science and communicating that I wanted to talk about is reproducible research. And you can think of it as this idea. You want to be able to play that song again. And the reason for that is data science projects are rarely one and done. Rather, they tend to be incremental, they tend to be cumulative, and they tend to adapt to the circumstances that they're working in. So one of the important things here, probably if you want to summarize it very briefly, is this: show your work. There's a few reasons for this. You may have to revise your research at a later date, your own analyses. You may be doing another project and you want to borrow something from previous studies. More likely, you'll have to hand it off to somebody else at a future point, and they're going to have to be able to understand what you did. And then there's the very significant issue in both scientific and economic research of accountability. You have to be able to show that you did things in a responsible way and that your conclusions